Welcome back to Algorithms. Today we're going to talk about the union find problem, a set of algorithms for solving the so-called dynamic connectivity problem. We'll look at two classic algorithms, quick find and quick union, and some applications and improvements of those algorithms. The subtext of today's lecture really is to go through the steps that we'll follow over and over again to develop a useful algorithm. The first step is to model the problem. Try to understand basically what are the main elements of the problem that needs to be solved. Then we'll find some algorithm to solve the problem. In many cases, the first algorithm we come up with would be fast enough. Maybe fits in memory, and we'll go ahead and use it and be off and running. But in many other cases, maybe it's not fast enough or there's not enough memory. So what we do is try to figure out why, find a way to address whatever is causing that problem, find a new algorithm, and iterate until we're satisfied. This is a scientific approach to designing and analyzing algorithms, where we build mathematical models to try to understand what's going on, and then we do experiments to validate those models and help us improve things. So first we'll talk about the dynamic connectivity problem, a model of the problem for union find. So here's the idea. There's going to have a set of n objects. It doesn't really matter what they are. We're going to use the numbers 0 through n to model our objects. And then we have the idea of a connection between two objects. And we'll postulate that there's going to be a command that says connect two objects. Given two objects, provide a connection between them. And then the key part of the problem is the find query or the connected query, which just asks, is there a path connecting the two objects? So for example, in this set of 10 objects, we've performed already a bunch of union commands, connecting 4 and 3, and 3 and 8, and 6 and 5, 9 and 4, and 2 and 1. And now we might have a connected query that says, is 0 connected to 7? Well, in this case, there's no connection, so we say no. But if we ask, is 8 connected to 9, we're going to say yes. Even though we don't have a direct connection between 8 and 9, there's a path from 8 to 3 to 4 to 9. So that's our problem, to be able to efficiently support these two commands for a given set of objects. Now let's say we add a union 5, 0. So that creates a connection between 5 and 0. 7 and 2 creates a connection between 7 and 2. And 6 and 1 between 6 and 1. So now if we ask, are 0 connected to 7? Well, 1 and 0, we can do that too. That's a redundant connection. And now if we ask, is 0 connected to 7? We're going to answer yes. So that's our problem. Intermix union commands and connected queries. And we need to be able to efficiently support those commands for a large number of objects. So here's a much bigger example. And you can see that we're going to need efficient algorithms for this. First of all, you can see we're going to need a computer for this. It would take quite some time for a human to figure out whether there's a connection. In this case, there is a connection. Now, the algorithms that we're looking at today are not going to actually give the path connecting the two objects. It's just going to be able to answer the question, is there a path? In part 2 of the course, we'll consider algorithms that explicitly find paths. They're not as efficient as union find because they have more work to do. Now, applications of these algorithms involve objects of all types. These are used for digital photos where the objects are pixels. They're used for networks where the objects are computers. Social networks where it's people, or computer chips where it's circuit elements, or abstract things like variable names in a program, or elements in a mathematical set, or physical things like metallic sites in a composite system. So all different types of objects. But for programming, we're going to associate each object with a name, and we'll just name the objects with the integers from 0 to n minus 1. That's a very convenient initial starting point for our programs because we can use integers as an index into an array then, and then quickly access information relevant to each object. And it also just suppresses a lot of details that are not relevant to union find. In fact, to make this mapping from an object name to the integers 0 through n-1 is a fine application of a symbol table or searching algorithm, which is one of the things that we'll be studying later in this course, algorithms and data structures for solving that problem. Now the connections, well, we need a few abstract properties that these connections have to satisfy, and they're all quite natural and intuitive. So we assume that is connected to is an equivalence relation. That is, every object's connected to itself. It's symmetric. If P is connected to Q, then Q is connected to P. And it's transitive. If P is connected to Q and Q is connected to R, then P is connected to R. Now these properties are very intuitive, but it's worthwhile to state them explicitly and make sure that our algorithms maintain them. When we have an equivalence relation, a set of objects and connections divide into subsets called connected components. A connected component is a maximal set of objects that's mutually connected. For example, in this small example here, there's 3 connected components. One consisting of just object 0, second one objects 1, 4, and 5, and third one the other 4 objects. And these components have the property that if any 2 objects in them are connected, and there's no object outside that's connected to those objects, those connected components, our algorithms will gain efficiency by maintaining connected components and using that knowledge to efficiently answer the query that they're presented with. Okay, so to implement the operations, we have the find query and the union command. And so we're going to maintain the connected components. The find is going to have to check if 2 objects are in the same component. And the union command is going to have to replace components containing 2 objects with their union. So for example, if we have these components and we get the command to connect 2 and 5, essentially, we need to merge the connected components containing the one containing 2 with the one containing 5 to get a big connected component. So now we have only 2 connected components. All of that leads up to, in a programming world, to specifying a data type, which is simply a specification of the methods that we're going to want to implement in order to solve this problem. So in our typical Java model, what we'll do is create a class called UF that contains 2 methods, one to implement union, the other one to implement connected, which returns a Boolean. The constructor takes as argument the number of objects, so it can build data structures based on that number of objects. And we have to bear in mind, as we're building our algorithms, that both the number of objects can be huge, but also the number of operations. We can have a very large number of union and connected operations, and our algorithms are going to have to be efficient under those conditions. One of the practices that we'll follow often in this course is to check our API design before getting too far into dealing with the problem by building a client that is going to use the data type that we develop. So for this example, we've got a client that will read information from standard input. First, an integer, which is the number of objects that are going to be processed, and then a series of pairs of object names. And what the client does is first it'll read the integer from standard input and create a UF object. And then as long as standard input is not empty, it's going to read 2 integers from the input. And if they're not connected, then it'll connect them and print them out. If they are connected, it'll ignore them. So that's our test client, and that's a fine test client to make sure that any implementation does what we expect that it will. So that's the setup. We've described the operations we want to implement all the way down to code, and we have client code that we're going to have to be able to service with our implementations.